Hello everyone, my name is Petr, this is Marek, and today we are going to talk about our journey from spreadsheet-like scheduling into the on-prem Kubernetes cluster. The talk will be divided into two parts, where in the first part I will try to tell you something about, or I will try to set you into the context and tell you something about our motivation to move to the Kubernetes cluster. And then Marek will continue by describing more technical details and technologies we use to build a cluster. All right, well, let's start with the context. Me and Marek, we are working for a company called Innovatrix, and more specifically, we are working for R&D department. And in the R&D department, we are training or developing machine learning models that are able to extract biometric features from pictures. So for example, you have picture with faces or fingerprints, and the model itself is extracting fingerprints or faces features from the picture. And to be able to train such models, me and Marek, we are building a platform. We are building it on premise. We are building on-premise, and the reason we have a special team is that we want to offload a software engineering job from our researchers. Now let's move to the motivation, and I will begin by describing some regular workflow of our researcher. Our researchers are starting by setting up the workload or training, then they are seeking for resources. After finding the resources, they are executing the workload or training. When the execution is finished, they are evaluating the results, and based on the results, they are editing or reconfiguring the training and repeating the process. And now let's move how it looked like 3 years before. 3 years before, we had this infamous spreadsheet, and you as a researcher just open the spreadsheet, put your name into the table, selected your resources, connected to the server, run to your workflow. And actually, for the researchers, it was great because you just connected to the server and run your workload. It was kind of straightforward. And also it was great because you didn't need any team to handle the spreadsheet and so on, so it was quite cheap. But the problem with this approach is that we are all lazy. So the spreadsheet was not updated at all. So at the end of the day, you needed to PM your colleague and ask whether the resource is free or not, and so on. And also, it has not any queuing mechanism. So you as a researcher, you are not able to plan your resources, your workload, and it has no fairness mechanism. So single researcher can allocate all the resources, and nothing is forcing him to use only part of the resources. And these cons leads to the poor GPU allocation. And in our case, it was around 50%, which is quite bad, to be honest. You can see it on the graph, where the average allocation is oscillating around 50%. By 50%, I mean that the GPU is idle for 50% of time. And fun fact about the graph is that we didn't have any metrics about allocation, so we needed to calculate it from temperatures. So we were observing temperature of the GPU, thresholding the temperature, and for example, when the GPU was over 60 degrees Celsius, we were considering it allocated. Sorry. And why do we taking care about allocation ratio? Actually, the reason is this guy, because he's selling us GPUs for a lot of money. For example, when we want to buy a server with mid-range GPUs, with modern mid-range GPUs, for example, NVIDIA 6000 ADA, it will cost you around $80,000. So it's quite expensive to have GPUs that are idle for 50%. And actually, that's the main motivation that was forcing us to move to the Kubernetes cluster, or introduce some kind of scheduling into our workflows. And yeah, and that's the reason why we implemented the Kubernetes cluster. And these are pros and cons we observed after we implemented the cluster. We were able to get over 80% of average GPU allocation, and that's because it has fairness mechanism, it has queuing, and also the Kubernetes cluster brought us a kind of simple implementation of monitoring stack. The cons are that the cluster needs to be maintained by someone, so we need to hire people, which is kind of expensive. And also, it is not possible, it's quite hard to have a same level of interactivity as you have with bare metal servers. You cannot just SSH to the server and run your workload. You need to provide some tooling because the Kubernetes have so many levels of abstraction. As you can see on the right side of the slide, we were able to get around 80% of GPU allocation. For some periods of time, we were able to get over 90%. That means for us that we need to buy new resources, and actually we did it based on this data. Yeah, I think that it's everything for me, so now I will pass my word to Marek, who will be talking about technical details.
Okay, thank you for the word, Peter, and now let's move to the current state and how did we manage to implement the queuing. So, at the heart of the queuing mechanism, there's a plugin into Kubernetes called Queue, which is a supplementary plugin to the default Kubernetes scheduler. And we also tried other options, which I will talk about them later. And why did we choose Queue? The first reason that it's really easy to deploy and manage, unlike the other solutions. It doesn't replace the default scheduler, it's just a plugin that it's working contemporary with the queue. And it also enables a fair sharing of the resources between teams with great visibility using Prometheus metrics, which I will show you on the next slides. And the other options we tried was Vulcano and Unicorn, and we didn't choose them because they are both of them replace the default scheduler. So everything that runs into the cluster has to use them, but if you use queue, just the resources you want are using the queue. The Vulcano also replaces the default Kubernetes job manifest with from their own API. So you have to replace all of your jobs with there. And Unicorn uses weird tree-like team hierarchy to set up the fair sharing. So we didn't choose them. And also queue is becoming the default CNCF queuing mechanism for queuing machine learning workload. For example, in the Google Cloud, they are using it for scheduling machine learning workloads. Using the data provided by Queue in the format of Prometheus metrics, we implemented this dashboard. The first row is showing average fair sharing value per team, meaning that the higher the number, the more resources is the team using, and the less likely will they come to schedule their workload. The second row shows the average waiting time per queue per team, and then in the third row there's the implementation of the queue itself, where you can see the name, position, when it was created, priority, and then if you would scroll more to the right, there's a description of why is the workload not being scheduled. So for example, one server is missing 1 GPU, other is missing 0.5 terabyte of RAM. So the researchers know exactly why is their workload not being scheduled. This is the schema of how the mechanism works. So researchers create standard Kubernetes job. Kyverno, which is a policy engine, I will talk about it later, automatically assigns and injects some labels needed by queue to work. Then it gets assigned to the team queue. Queue is in the background calculating the fairness score, which I showed here in the previous slide. Then it sorts the most top jobs are sorted, and if there are multiple jobs that would fit into the free resources, the one with the lowest fair sharing value is picked. The team gets assigned the server resources. They are marked as used by the team itself. The fairness score is recalculated, and queue injects, based on the selected node, queue injects the node selectors, and then it gets passed to the standard Kubernetes scheduler, which just scheduled the pod itself. So that's for the running batch jobs, which can take anywhere from a few days to a few weeks. And how about interactive development, which Petr mentioned in one of the cons of running the Kubernetes. So we solved that by using Coder, which is like a developer portal where you can spin up development environments in Kubernetes. It's a website which you run inside Kubernetes, and you spin up the environments. I will show them in the next slides. You get a single entry point for all of the servers inside the cluster, and you also get the usefulness of being able to open the pod remotely inside of the IDE of your choice. So we are using Cursor or VS Code, but there are many plugins, including IntelliJ, etc. You can also open a terminal from the web browser or SSH into the pod itself. And what's really great benefit that it eliminates the end user environment setup time, because everything is pre-prepared and you just fill in some values. So how it works. The researcher logs in using Google SSO into the website. They fill in some values for the template. At the background there's Terraform running apply. The Kyverno assigns automatically some labels. Then the whole process, which I showed previously with Q, is applied also, and then it gets passed to the default scheduler. Pod is scheduled, and in the background of the pod, there is a coder agent running, which enables all of these functionality. And this is how it looks like. So you have a catalog of templates which are written in Terraform. We are using devpod, which is standard pod using deployment. And you also have the capability to use dev containers in Kubernetes. So the benefit of this is that you don't have to have the image pre-prepared. It gets built inside the pod itself, and then the coder kind of injects the image into itself, and after the image is built, then the pod itself is run on the image. This is how the template looks like. It's just a standard Terraform template, which you can use. You can use their template and customize it, which we did. This is the interface that the end user is going to open. Fill in your namespace, which repository you want to clone, etc. Then Terraform apply and plan is run. You then have this environment, which you can have as many as you want. And using Kubernetes deployment scale down and scale up, you can stop or start the environment. This is the pod running itself. So there are some scripts running from the coder agent. You get the resources, and you can open the environment inside VS Code, Cursor, terminal, or standard SSH. You can also embed this environment into your Git repository. So you just log into the Git, click on this open encoder, and your environment is spin up automatically with pre-filled values. So you can get instantly coding. Supplementary to this, we also implemented our custom notification system, which is just a Google Chat bot that sends you status of your job. So when your job is marked as completed or failed, you get the status in Google Chat, which says how many resources did you use, and how many resources should you use next time you schedule this workload. We implemented this because researchers used to hog a lot of resources that were not used. So they requested, for example, 25 CPUs, but 95 percentile of the time they used only 5. So we needed some mechanism that would solve this. So this is just a simple Python web app running inside our cluster, and at the background there are Grafana alerts being sent to them, and using Prometheus metrics history we can provide this functionality. That was the part that is facing the researchers, and now let's more talk about the infrastructure powering it. So at the heart we are using Argo CD, which is a GitOps staple, I think. I believe it's far better than Flux. Yeah, that's just my opinion. What is GitOps? GitOps is an idea where you store all of your configuration inside Git, and then you use some mechanism to reflect that configuration with reality. So you define all of your applications inside Git, then Argo CD comes and syncs it into your cluster. At the background, those are application manifest standard YAMLs, and the background Argo CD is calling Helm template and then doing diff versus the reality. What are the benefits? You get, you can see all of the changes going through pull requests, and contemporary to this, you get no configuration drift because it syncs automatically. You get reproducible and consistent environments or deployments. So in case of disaster recovery, you are really quickly able to go back to the state previously, and also you get native rollback capabilities. We also using Argo. We are storing all of our secrets inside Git using sealed secrets, which is a service that encrypts all of your secrets using Kubernetes clusters certificate authority, so you can decrypt and encrypt all of your secrets only in the target cluster, so it's safe to store those passwords inside your Git. This is the UI of the Argo. You can see that at the beginning there was the app health was missing, so some resources were not in the cluster that are defined in Git, and you can either sync it or it gets synced automatically in a loop which is running every minute. And what about observability? We implemented it using LGTM plus Alloy, which is a Loki, Grafana, Tempo, Mimir. We are not using Tempo because we don't need races. And what are the benefits for us and for the researchers? So when we need to buy new hardware, we have a concrete evidence when the resources are overutilized, so we know exactly when we need to buy new hardware. This actually happened a few times already. The researchers knows on which server are the resources free, so they know what can they afford to use. And contemporary to that, the resources are optimized because, yeah, never mind. And it's really easy to solve some problems using Loki because of its capability to use regexes and some rules that you can write to extract all of the logs inside of the cluster. And this is how it works. So you get Grafana Alloy, which collects logs and metrics. Metrics are pushed to Mimir, logs are pushed to Loki. Loki is pushing them with Mimir to our external Minio, which is a set retention 1.5 year for metrics and 30 days for logs. And then the researchers are using Grafana as UI. This is our custom dashboard, which used metrics pulled from Q, which shows the server and how many resources are free. So CPUs, memory, ephemeral storage, and GPUs. And this is our second dashboard, which is like for admins, well, for me. And here, I don't know if you can see it, but the main point is that what is blue or green is okay, what is red is bad. And we have this opened alongside in our office. So at the first glance, when I come to my desk, I know if anything is wrong with the cluster. We are also using many other technologies that I didn't mention. I will try to go through some of them. So as a Kubernetes distribution, we are using RKE2, which is a simple one binary setup, where if you want to install or upgrade the Kubernetes, you just replace the binary. We are using Ansible to distribute it. Longhorn is used as our persistent layer that is running on our control plane nodes, which is storing the write-ahead logs from Loki and Mimir. So in case of your S3 goes down, The logs and metrics are stored locally, and when the S3 comes online, then they are pushed. We are using also NVIDIA GPU operator to schedule the GPUs as native Kubernetes resources. It manages drivers, CUDA versions, etc. Calico as network interface, and Kyverno as the policy engine to mutate and distribute some config maps and secrets to these researchers, so they don't have to set up their environments manually. And even then, there are many more technologies that are either not that interesting or I wouldn't be able to fit it into time frame. So that brings us to the conclusion. What did this implementation, where we went from one spreadsheet and separate Ubuntu servers to the one platform, brought us? So as I mentioned, we now have historical metrics for decision about buying new hardware. The GPU utilization went from about 50% to about 85%, and it's increasing. We have a single point of entry to all of our servers, using the queue for the batch jobs and using Coder for the interactive environments. All of the nodes, or all of the compute nodes, are stateless because the data which is used by those machine learning workloads is stored on our centralized all-flash storage running NVMe drives. So in case of disaster recovery, you can spin up the node back online when the hardware gets replaced and OS installed. You can get it running back into Kubernetes in 5 minutes because you just distribute one binary and the configuration is stored on the control plane nodes, which are run in high availability. You also get almost no configuration drift because on the layer of Kubernetes, it's managed by Argo, so there's no drift. But I say almost because it can happen when you run Ansible against the servers and you do something manually on the servers. And also jobs can be added to queues with fair scheduling, which is the main benefit for the researchers. What did we learn in this journey? I wouldn't use Ubuntu if I would do it again. I would use Talos Linux, which is a CNCF operating system, which doesn't have any SSH access or some command line. Everything is done via their API, and you can. It's declarative and atomic, so every operation you do is either completed or rollback automatically. And you can also, it's a declarative, so you specify everything that you want to have on this OS, and it then gets using the API, it gets translated to reality. I couldn't use it at the time because there were some issues with NVIDIA drivers running on Kubernetes. But right now, I would 100% go with Talos. I wouldn't use customize for user workloads. It's pain in the ass to manage. You have to patch the YAMLs. You cannot use some templating or variables. So I will go with Helm, just running Helm template, not install, just using the templating part. But we are not still sure about that. Focus on interactive workload. If you just run the batch workloads, it's not enough for the researchers. They need to have interactive access to the resources as well. Give feedback about the used resources, because otherwise the researchers will hog them and they don't care if they request 50 CPUs and use only 10. You have to inform them proactively. Use centralized storage instead of stateful nodes, because if you use stateful nodes, for example with Longhorn, you get problem with data locality, and then you have to use NFS, which is really slow for running those workloads. It needs to have really fast access to data. So we transferred from stateful nodes to stateless nodes with centralized storage. Hide complex stuff behind simple interfaces, meaning that the researchers don't want to write their own deployments for the pods and applying them manually. They want something they can click and have it spin up. So that's why we use Coder. And also onboard as fast as possible and as simple as possible, because if you have a lot of manual steps, they will get angry and you will have a lot of tickets. So everything that can be automated, and yeah. That's about all from us. And now it's time for Q&A if you have any questions. So you asked how big is our infrastructure. So we have 3 control plane nodes running in Proxmox as VMs in high availability. And we have about 10 on-prem servers which are running bare metal Kubernetes. You mean that if the yeah, you can run it, but I wouldn't use RKE2. I would use, for example, K0S, which is a lightweight distribution. You can run it on a single node. You don't need any control planes. And the queue itself can be run on only one node. And you will still get the fair sharing benefits.
I'd like to add something. I think that it's totally feasible to run it on one server. But maybe you can focus on deploying some finished solution, not to make it by yourself. For example, like 3 months ago, NVIDIA introduced Run AI scheduler, which can be deployed on your infrastructure. So maybe that's more suitable way for you, I guess. I don't know. Maybe we can talk about it later after presentation.
Okay. Any other questions? Sorry. In our current state, when we have the so you asked how difficult was it for researchers to switch from scheduling on the spreadsheet to Kubernetes. This final state that we have now was iterative. So at the beginning, they had their own, for example, the coder environment was before standard Kubernetes deployment. So it was pain in the ass for them and for us also. So at the beginning, they didn't want to switch, but as we iterated, it's nowadays it's not pain in the ass. You can spin up or you can set up your environment in 3 commands and everything is done. So right now it's really easy for them. But at the beginning it was not.
I'm going to add something again. I would say that you need to motivate them by adding the most performant servers to the cluster. Then they are forced to move. But yeah, we were iterating and trying to reduce obstacles at tooling that is able to abstract the complexity. So right now, actually, we were not able to put it into the presentation because we thought that we are not going to make it on time. But we implemented some kind of CLI tool that is able to abstract all the complexity, and they are just putting some parameters to the tool, running apply, and it's deployed to the cluster. So that's probably the way, but it was working for us.
Yeah, I would add that what Petr mentioned is our tool in Python, and it abstracts Docker build, Docker push, kubectl apply, kubectl validate, that kind of stuff in one command. Okay. So you asked if we'd consider some more standard approach like Airflow or something. No, we did not. We did, but it would require to rewrite all of the scripts that were previously ran by the researchers as just as SSH commands. So we almost exactly took them one to one and encapsulated them into the Kubernetes, so it was easy to transfer from the current previous state to nowadays state.
I will add something again. Actually, we are using Argo workflows to do batch scheduling, so it plays quite well with Q, Marek was talking about. So yeah, the stack we implemented is integrated with some kind of batch scheduling tools that we are using Argo workflows. Yeah.
I would like to add something that we are in the first steps of using Argo workflows, so that's why I didn't mention it. But the pipeline capabilities of running Argo workflows are really good. For example, the Kubeflow engine that is like now the staple in running machine learning workloads, it's using Argo workflows in the background. But the downside of Kubeflow is that you have to use the whole cluster only for Kubeflow, nothing else. So that's why we didn't went this way. So you asked how, with nowadays knowledge, how would I make the transition as smooth as possible? I would go the same way as I showed you now. Actually, maybe force the Argo workflows and use the Talos Linux instead of Ubuntu, but I'm not sure if I would change that much.
Yeah, my 50 cents. From user's perspective, from researcher perspective, we would probably use the same process or deploying incrementally, but maybe we would avoid the customize, which is bringing a lot of complexity to the for the researcher, and maybe with Helm we would be able to provide them more user, better user experience. So because the reason why we have implemented abstraction, I've been talking about 50 minutes ago, the CLI tool that is helping the researchers to deploy the workload was probably created because the customize we needed to encapsulate the complexity. So maybe with Helm it would be more usable for researchers. So the adoption would be probably better or faster, but do it incrementally. That's
just to add another thing, if you would use Argo workflows, you don't need to use Customize or Helm. You can use Hera, which is a Python framework that translates Python code to the Argo workflows YAMLs, and you can deploy the batch workloads directly from Python into the cluster.
Yeah, that's important. It's in Python, and all researchers are working in Python, so that's probably the way to go. Is there any other question? If not, thank you for your attention. I believe you are all hungry, so thank you.